Hey everybody, it's Mrs. Cassell. I'm ready to take your beautiful foldable here and turn it into a free body diagram. The first thing I'm going to do is I'm going to pick the object on which our forces are going to act, that we are going to analyze, and I'm going to draw that object right here. I'm going to pause this and use movie magic. Boop! Hello, this is Mr. Cat. So you could have drawn whatever animal, object, thing you want. You could draw a box for all I care. If you have a favorite animal that is different, you draw it. So Mr. Cat is going to be the object here on which our forces are going to act. He's missing something. I think he needs a bow tie. Yeah, that definitely looks better there. A little more dapper. Yeah. Lopsided. Perfect for a cat. I want him to be happy, so he's been set free, and he's sitting out on a sunny day, unlike today, out on green grass outside. He's not running away. He's just hanging out on the ground there. And there we go. That's our object that we're going to analyze our forces on. Now, we've got 4 tabs here, which means you can guess we're going to label just 4 forces today. There's obviously more that we could think about, but we're going to use 4 as an example. Now, while we might be analyzing the forces on an object that's a real object, like a cat, that's certainly not what we draw when we draw a free body diagram. Free body diagram is a scientific tool for analysis. That means we want to simplify the bits and pieces of that tool that we can. So a free body diagram, instead of drawing the object, it's no longer a picture of the Mona Lisa petting a fuzzy kitty and analyzing the forces on it. We draw a dot, a circle, or a box. So here we go. This just became my cat. Sometimes we label that dot or object with useful information like the mass of that object. Because remember, what forces are is the ability to accelerate an object or the ability to accelerate mass. So this is our object, therefore it is the mass that we are considering. So, the first force you might think about, the one that everybody knows, Mr. Kitty here, Mr. Cat is sitting on the ground, therefore the first force acting on him is the downward acting force of gravity. We label forces with a capital F, followed by a little subscript that denotes what they are. But the force of gravity also goes by another name that you have heard before, but is now an official technical designation. The word weight in physics means the force of gravity. So, weight and force are not synonyms. This is one of the most important things to learn if you learn anything from physics at all this year. Or, excuse me. Oh, I just said weight and force. Scratch that. Remove it. What I meant to say was mass and weight have been terms that in regular life up till now you have used these two terms synonymously. Mass and weight are not equivalent terms. Weight is in fact a force. Mass is the amount of matter in an object. So weight is the force due to gravity acting on an object. What does that object have? Mass. What does the force of gravity do? Accelerate that mass. A couple things about it. Forces are vectors. They act in specific directions. So, the direction for the force of gravity is always toward the center of the Earth. Now, you might be asking yourself, hang on, what about if I go somewhere else in outer space? Sure. What if I'm talking about a giant halo that I've built that is my space station on which I live now? Absolutely. We're also talking about the center of mass. We'll learn more about this later, as well as how gravity works between masses that are not just the planet Earth and bowling balls and things that we're rolling around. But in the meantime, you know that the acceleration of gravity, which we have been using a little g to abbreviate, is a value that has been constant. We'll show where that value comes from later. So the force of gravity, or the weight, is the first force that we're identifying acting on Mr. Cat here. Now, how come Mr. Cat isn't plummeting down to the center of the Earth here? If he's being pulled towards the center of Earth's mass, shouldn't he be going and accelerating this way? Well, good job. I heard it. I sensed it that you were saying it. There is, in fact, the ground preventing him from doing so. There is an equal and opposite force acting upwards on Mr. Cat called the normal force. Now, it's not called the normal force because it's ordinary or everyday or it isn't special or anything. It has to do more with defining mathematically what's happening. The normal force is a contact force. It's exerted by a surface. So Mr. Kitty is sitting on the ground here. So since he's sitting on a surface, that surface exerts a force on him. That's why you're sitting in your chair right now, and you also are not plummeting down to the center of the earth. Instead, the ground is pushing up on you. We call this the normal force because the word normal in mathematical terms refers to a perpendicular angle. So the normal force is always perpendicular to and away from the surface. So in this case, we have a surface like this. So the direction of the normal force is always going to be a 90-degree angle from that surface. If I take Mr. Cat here and I put him on a hill, the normal force is still perpendicular to the surface. Our surface is now angled, but if we measure a 90-degree angle, that's the direction of the normal force. If we think about this for a second, the center of the earth is still below Mr. Cat on the hill. So the force of gravity is now acting downward, right? So we now have a force which is not met by an equal and opposite force. What keeps Mr. Kitty from sliding off the hill right here? What allows him to stay stationary right there? You guessed it. The third force we're going to add. There's some force that's opposing the possibility of his slide. That is the force of friction. And friction comes in two flavors, static and kinetic. We'll be analyzing each separately later. But friction has some general definitions. Friction is a contact force, just like the normal force. Gravity is a field force. You can all demonstrate friction just by rubbing your hands together. It's a contact force that opposes sliding motion. So if you take your hands and attempt to slide them against each other, you create friction. There's energy loss there that creates heat. Oppose is part of our directional information here. Friction is always a force that is parallel to the surface and in the opposite direction, hence what the word oppose is doing in the sentence above. It's in the opposite direction of motion. So Mr. Kitty, sitting on the ground here, when we turn our surface this way, here is our surface. Parallel to that surface will be the force of friction. If this is the direction that gravity would be accelerating him, because this just became a ramp, right? There is some component of the gravity that's going to be acting in that direction. Then the force of friction is acting to oppose that motion. Now, you can imagine that if we turn this into ice, if we turn this into gravel, if we turn this into sticky chewing gum, it would change how much force of friction there was. So the other thing about friction is it depends on the materials. And we use something called the coefficient of friction to determine just how much friction there is. These are values that are determined experimentally. There is no divine natural order by which those coefficients are described. It's something that we test and measure. We use the Greek letter mu, which looks kind of like a Y combined with a U, but if you look closely, it kind of looks like a fancy M, hence mu, to represent that number. And a coefficient is just a number. We'll learn more about those later. So, Mr. Kitty sitting on the ground right here, even if he is sitting on level ground, that moment comes with every pet, for those of you who have to walk dogs, where you say, ooh, come this way with me, please. And you would like to move your pet in the direction of your choice. So, if we were to attach a leash to Mr. Cat here and give him a pull, we'd be adding our fourth sample force to our free body diagram here, which is we have now created an applied force. Now, applied force can have all sorts of names. Let's think about what we could name this force right here. It's the force of our pull. We could abbreviate that F with a little p. If we were using a leash, there would be tension in our leash, right? We could be defining that as the force of tension. We could be defining it as the force of the leash. We could be Jedis, and we could be using the force. The name of the force isn't important. The point is we have applied a new force to this otherwise static system. So, what we have now are 4 forces acting on our cat. All of those forces add together to create something called the net force. This is what Newton's second law is all about. Newton's second law says that the net forces acting on an object are what will result in the acceleration of that mass. In other words, when you see an object changing its state of motion, that change is the result of all of the forces on that object added together. So net force means the sum of all forces that are acting on an object. That includes in all directions, so we will be studying two-dimensional sums of forces to find our net forces. Now, here's the thing. Those of you who have big dogs, or even little dogs for that matter, you've all had that moment where you're trying to get your dog to go where you are pulling on the leash and the dog does not move. If you see an object with 0 changes in state of motion, that means there is 0 acceleration, which means our net force is 0. What happens if I take that applied force and I make it a whole lot bigger? What happens if I take that applied force and I make it a whole lot bigger? Well, I've already stated that my normal force is equal to and in the opposite direction of my weight if I'm sitting on a level surface. The force of friction is determined by a coefficient of friction that's about those two materials, which means that there is an amount of pull that I can put on Mr. Cat's leash that will cause him to accelerate in this direction. If we take our leash here and we put in our maximum effort, we will now unbalance the forces on him. When an object has balanced forces, we call that being in equilibrium. When those forces are unbalanced, that's when we see change happen. If there are unbalanced forces, this is the direction that an object will accelerate. You already know this. If you shove your lab partner, they're going to fall out of their chair in the direction that you shove them. If you pull them, they're going to accelerate out of their chair in the direction that you pulled. So whichever direction the net force is acting in is the direction that the object will accelerate.